So our exponential function. Okay. So what we're interested in is differentiating exponentials. Okay. Now, how are we going to do that? Well, function x, I'm going to define to be a to the power of x, so our basic exponential function. That means function x plus h is a to the power of x plus h. Okay. So I can now use my first principles formula. So whenever we've got a new function and we want to work out how to differentiate it, we go back to first principles and sub that in. So we get limit as h approaches 0, a to the power of x plus h minus a to the power of x. Well, I can factorise the top and I get a to the power of x outside of a to the power of h minus 1 over h. The problem is, if I substitute 0 into that, I can factorise out the a to the power of x, because h is not going to affect that. So it's sort of like it's a constant as far as h is concerned. So I can factorise that out of the limit. And this limit of a to the power of h minus 1, well, if you think about it, if we sub 0 in, I'm going to get a to the power of 0, which is 1. And we get that problem again of 0 on 0. So the question is, how on earth do we find this limit? So let's just look at that limit. So there it is. Limit as h approaches 0. I'm actually going to rewrite it a little bit strange. So instead of a to the power of h, I'm going to write it as a to the power of 0 plus h. And instead of 1, I'm going to write it as a to the power of 0. Now those two expressions are equivalent. I've just written them in a different way. But if you have a look at the form of the right-hand side, that actually is our first principles formula. It's just that instead of writing x, I've got 0 there. Right, so in other words, what I'm saying is I've got function 0 plus h minus function 0 all over h. So that expression would be the derivative at the point where x equals 0, or the y-axis. So this limit will be equal to whatever, I mean, I don't know what it is, we're going to have to work that out, but whatever the slope of the tangent is at the y-axis, or when x equals 0, that's what that limit will be equal to. So all right, so function x is a to the power of x. The derivative then, well, I'm just going to call it m for slope. So it'll be m times a to the power of x, where m is the slope of the tangent at x equals 0. It's not a great formula, but at least we've got something to work with. So Euler's number is E. E for Euler, I guess. It's basically an irrational number. Just like pi is an irrational number. We don't know what it is exactly, but it is defined as the limit as n approaches infinity of 1 plus 1 on n to the power of n. So as you substitute in bigger and bigger numbers into that 1 plus 1 on n to the power of n, you get closer and closer to the value of e. Now, of course, you can never get there because it's an irrational number, and irrational numbers never end, they just keep going. But if you were to go to your calculator, you'll end up with something like that. Even a spreadsheet, pretty much, that's the limit without it going into scientific notation. 2.718281828, which is really unfortunate because it looks like it's repeating. But if our calculator could handle more numbers, you'd see that actually it does break into a different pattern. It doesn't keep going 1828, 1828. It keeps going with other numbers. But that's approximately the value. Okay. So we're really interested in the exponential function base e. Base e. And the way it's defined is simply that. We will define it to be the function that has a slope of 1 at x equals 0. So now we know how to differentiate e to the power of x, because we said it was going to be the slope. Well, f dash 0 we've just defined to be 1. So our derivative will be 1 times e to the x. So it's a really interesting function in that the derivative, or the slope of the tangent, is the same as the function itself. So graphically, if we were to look at it, what we should see is that at any point on our curve, the slope of that basic exponential function, now this is only true for base e, if it was base something else, that slope would change. But it would be equal to the height of the curve above the x-axis, or the y value. And so that explains why exponential curves get steep really, really quick, because the y value is going up, so now the slope increases, which means it goes up quicker, but then the y value gets bigger, so it gets quicker again, and creates our exponential function. So let's say another way of writing it simply is, well, the derivative would be the y value. If I was to write it in terms of y instead of in terms of x. Okay. Now, on your calculator, I don't know how much you've used Euler's number yet, but there is a button on your calculator that will find it. You'll notice on there e to the power of x. So if you had to find e cubed, it's not rocket science, we just go to our calculator, oh, what's e cubed? And you should get something like that, 20.086. If we had to draw the curve, y minus e to the minus x, so back to our basic curve sketching ideas, I'd look at that and say, well, the basic curve I'm drawing is our basic exponential, base e to the power of x. Okay, so it looks something like that. Now it's e to the minus x. So when it was function negative x, we reflected in the y-axis. So all right, let's flip that over. So it's e to the negative x that I'm interested in. But then it's minus that again. So now it's minus function x, and that's when we reflected in the x-axis. So now we'll flip it that way. So we've now got minus e to the minus x, and the last thing we have to do then is we're going to shift the whole thing up 5 units. And so there we go. There would be y equals 5 minus e to the minus x. All right, that's really all I'm going to say today about exponentials. So 11a, you notice I've only put 2 questions there. So 1 and 2 is more a practical one where you actually sort of estimating the slope. I've reprinted there the grids from the textbook, which should be on the next couple of pages, so that way you don't have to try and not dirty up the textbook. You can use that to do that. And then 11b we'll play with as well.